Hi guys, it's me Sir Ernest, and today we will solve problem 7.1 of Griffiths 4th edition. The problem reads, two concentric metal spherical shells of radius A and B, respectively, are separated by weakly conducting material of conductivity sigma, as in this figure. If they are maintained at the potential difference V, what current flows from one to the other? And what is the resistance between the shell? Letter A. So let's assume that the charge within the inner shell is Q. Okay, so that the outer shell will be negative Q. Okay, so from here we can see that the electric field is now radially outward. And that is said to be uniform. Now, the first thing that we need to do is to know the potential difference V due to the configuration. Now, by Gauss' law, the electric field inside the conducting material with conductivity sigma is determined by first identifying the Gaussian surface, because we're going to use the electric field to calculate the potential difference. So as you already know, that for this kind of system, the Gaussian surface that we're going to use would be a spherical Gaussian surface with radius r. So by Gauss' law, where it states that the closed integral of the electric flux E dot dA is equal to Q enclosed over epsilon sub 0, because this Gaussian surface encloses this charge Q, so this is equal to Q over epsilon sub 0. Because of symmetry, this integral becomes a simple multiplication of the electric field, which is uniform, times the total area of the spherical surface, which is 4 pi r squared, and this is equal to Q over epsilon. So therefore, the electric field will now be equal to Q over 4 pi epsilon sub 0 r squared r hat. So therefore, the potential difference, which is defined as the integral of E dot dr from B to A, is equal to the integral of this one. So this is negative. If you want this integral to be positive, we just swap the limits of integration. So this becomes A to B, and then E would be Q over 4 pi epsilon r squared dr. Okay, noting here that dr vector is dr r hat. So r hat dot r hat would be equal to 1. Okay, so the potential difference is now calculated as follows. So this is Q over 4 pi epsilon sub 0 times the integral of dr over r squared from A to B. So this is equal to Q over 4 pi epsilon sub 0 times negative 1 over r evaluated from A to B, or simply Q over 4 pi epsilon sub 0 times 1 over A minus 1 over B. So this is the potential difference. So therefore, the current that flows will be equal to 4 pi epsilon naught V all over 1 over A minus 1 over B. Now, so let's take note of this. Now let's compute for the currents. Current I for this closed surface will be just a closed integral of J dot dA. So this is a surface integral for this surface. So this is a definition of your currents. Current by Ohm's law is equal to sigma E dot dA, which is equal to sigma times the equal of E dot dA, which is Q enclosed over epsilon sub 0. So this is sigma times Q enclosed over epsilon sub 0 from Gauss law. And Q is given by this. So this is sigma over epsilon times 4 pi epsilon V all over 1 over A minus 1 over B. So from here, so therefore, the current I will now be equal to, so epsilon naught cancels, so this is 4 pi sigma divided by 1 over A minus 1 over B times B. Okay, so here the current is now in terms of the inner and outer radius A and B, conductivity sigma, and the potential difference between the two shells. Now for letter B, the resistance by Ohm's law, this is now equal to I equals V over R. So therefore, the resistance for this configuration is now given by 1 over 4 pi sigma times 1 over A minus 1 over B. So again, our resistance between the shell is a function of just the inner and outer radius together with the conductivity. We can also express this in terms of resistivity, where the conductivity is just the reciprocal of the resistivity. So the resistance will now be equal to rho, that's the resistivity, divided by 4 pi times 1 over A minus 1 over B. So as you will notice here, I express our my answers, our answers, in terms of the given variables. Okay? So that's it. That's problem 7.1 of Griffiths 4 edition. Okay? So I hope you learned something today. Thank you guys for watching. And I'll see you guys in the next video. Bye-bye.